Now we'll start talking about Weil's proof. Compared with Haar's original idea, by dealing with measures of sets directly, Weil's proof utilizes integrals of functions instead of measures of sets. And this, in general, is a very beautiful idea in modern real analysis. In modern real analysis, instead of studying the measure of a set directly, we'll transform it into the study of an integral of a function. Specifically, Weil's idea is the following. If two functions, f and phi, are in CC plus G, this notation means the collection of all compactly supported continuous functions on G that are non-negative and the supremum norm is strictly greater than 0, meaning f is not identical to 0 on G. So here I should give a footnote. This means compactly supported continuous function and this notation means the supremum norm for f. For these two functions, maybe here we should not use the letter f again, but never mind. I guess you guys know what it means. We are just picking two arbitrary functions in CC plus G. Now we will define the analog to the Haar covering number of f with respect to phi. And remember, in Haar's original idea, this E column B is what I meant by Haar covering number. Maybe I should write this down. And now we will define the Haar covering number for functions as opposed to sets. F column phi is defined to be infimum of the sum of the coefficients of C sub j's from j equals 1 to n, where those coefficients come from here. F less than or equal to the summation of Cj times Lxj of phi, which is from 1 to n. I'm going to explain this notation soon. But let me first finish this sentence. For some positive integer n and x1 through xn in G. Now let me explain this. Some of you might have already seen this many times. This means a left translation of the function phi on the topological group G by xj, which is an element in G. But let me write this down. So left translation of phi by xj acting on y will be equal to, by definition, phi of x sub j times y. So what are we doing now? We're considering all possible linear combinations of left translations of phi so that this linear combination will be greater or equal to f. Analogous to the idea of covering, as in the situation for sets. And remember, the covering of sets or the containment of sets will be really translated into the greater or equal, less than or equal to notion in terms of characteristic functions. A set is contained in another set is same as saying the indicator of the first set is less than or equal to the indicator function of the second set. So I guess it is not so hard for you to understand why this is really kind of based on the Haar's original idea. And that is also why we introduced Haar's original idea at the beginning, because it really helped motivate Weil's idea. Now, if you just look at this set and this infimum, namely the definition of f column phi, there are some basic questions you might want to ask. Those questions should be like mathematical instinct for you. I'll let you think for a while what questions you want to ask. And then I will tell you the questions. But just looking at this set, you might want to ask, could this set be empty? Whenever we define a set in a very complicated way, the first question that we might want to ask ourselves is whether that complicated set could be an empty set. Otherwise, if after a lot of great effort, we only find in the end that we defined an empty set, that's too embarrassing. So, is this set empty? So the first question we want to ask ourselves is that, could this set be empty? The answer is no. And as a consequence of this set being non-empty, we must have this Haar covering number is finite for every f and phi in C plus G. So why must this set be non-empty? Let's prove it. In fact, for fixed f and phi, and for any epsilon greater than 0, but at the same time less than the supreme norm of phi on G, remember this guy is always a non-zero number. So we can choose epsilon less than this. Now for any epsilon between 0 and this number, we consider the following set. The set U sub epsilon, which is defined by the collection of points in G, such that phi of x is greater than the supreme norm of phi minus epsilon. Since phi is continuous and compactly supported, the supremum of phi can be reached at a certain point. So, this set must not be empty, because you can always find in the punctured neighborhood of the point where phi attains its supremum, so that phi of x is greater than that supremum minus some epsilon. And clearly, by the continuity of phi, this set is open. And of course, this is for any fixed phi in CC plus G. So this is for phi. And now let's turn to look at this f. For f in CC plus G, since by definition the support of f is always compact, so there are finite many elements x1 through xn in G, such that the support of f is less than or equal to, is contained in the union of the left translations of this u sub epsilon defined above by xj's. So how is the compactness used here? Without compactness, we may want to consider all elements in G, and we can take a possibly infinite many left translations of u sub epsilon by all elements of G, which clearly cover support of f, because that union will be essentially the G itself. In particular, it covers support of f. But because support of f is compact, we can reduce the infinite cover to a finite cover. And now, in order to show that this set is really non-empty, let us make the following claim. We claim that there's the following inequality: f less than or equal to the supreme norm of f divided by the supreme norm phi minus epsilon times the summation of all such left translations of phi, j from 1 to n. The left translates of phi by x sub j inverse. Because they are group elements, we can take inverse. And as a consequence of this claim, the sum of coefficients will just be, in this particular situation, n times this constant. Now let's prove this claim. Indeed, for any x in G, if x is not in the support of f, then this inequality trivially holds, since then f of x will be 0. So left hand side is 0. And of course, the right hand side is always greater or equal to 0. And now, if x is indeed in the support of F. Then, since, remember, support of F is contained in the union of xj's times u sub epsilon, which is from 1 through n. We can write x as a product of x sub I and x sub epsilon for some I from 1 to n and x sub epsilon in u sub epsilon. This containment comes from here. Now, what does this mean? What is the meaning of x sub epsilon being in u sub epsilon? This part means phi of x sub epsilon is greater than the supreme norm of phi minus epsilon. This is how we defined u sub epsilon up here. So it follows that if you consider this quotient, the sum of left translations of phi acting on x divided by the supreme norm of phi minus epsilon. This guy, remember, x is equal to x sub I times x sub epsilon. So this sum, because each individual term is non-negative, is greater or equal to, in particular, each individual term. So this is greater or equal to some L sub xi inverse applied to phi acting on x sub I times x sub epsilon. Again, divided by the supreme norm of phi minus epsilon. And if you simplify this, so xi inverse and xi cancel out. So this will give you phi of x epsilon in the numerator, and this is divided by the supreme norm of phi minus epsilon. But this guy, by the fact that x epsilon is in u epsilon, will be strictly greater than 1. And thus, we get what we want. At f of x, which is of course less than or equal to its supremum, will be again less than or equal to this quantity. Because this guy over this is just proved to be greater than 1. And this verifies our claim. And remember, our claim implies that this set must not be empty for any f and phi in CC plus of G. So this answers our first question. The second question that we could ask is the following. Could this Haar covering number f column phi be 0 for some f and phi in CC plus G? We ask this question because later on we will take the quotient as an analogy to the Haar's original idea of utilizing the unit measure or unit covering number. And in order to let quotients make sense, it would be great if we have non-zero covering numbers for all f and phi in CC plus G. The answer is no. F column phi will be non-zero for any f and phi in CC plus G. That is great, because then we'll be able to take quotients. Indeed, we can make the following claim. We claim that if f and phi are both in CC plus G and they satisfy the inequality that f is less than or equal to the summation of C sub j times the left translation of phi by x sub j. The sum is taken from j equal to 1 to n for some positive integer n and group elements x1 through xn in G. Then we're going to have a lower bound for the sum of coefficients. This guy will be greater or equal to the supreme norm of f over the supreme norm of phi. And in particular, this is greater than 0. Because f and phi are both in CC plus G, by definition, this numerator will be greater than 0. This claim is easy to verify. Indeed, suppose otherwise, the sum of coefficients C sub j's is less than this quotient. Then f of x is less than the summation from j equal to 1 to n C sub j times the left translation of phi by xj acting on x. And this guy is further less than or equal to the sum of all coefficients times simply the supreme norm of phi, which, by our assumption, is strictly less than the supreme norm of f. And this is true for any x in G. So we get something that leads to a contradiction. We conclude that any x in G will make f strictly less than its supremum. But this is absurd because f is in CCG In particular, is complex supported, which implies that there exists x0 in G such that f of x0 is precisely equal to the supremum. So we get the contradiction, which verifies this claim. Because the origin of this contradiction is from this assumption. If assumption fails, then the claim holds. So this answers our second question.